Hello TCMS, glad to have you all back here for another video session. Today's material will be on combinations, and I continue to hope that the videos provide the support you might be needing as you navigate your way through Unit 3. I know Unit 3 is material that many of us have never seen, but judging by your Schoology submissions and discussions, I would say that you're doing a phenomenal job of making sense of the math. I especially appreciate those of you that in this instance where you might not get it right the first time, you're really taking the time and making the effort to fix your assignments and submit them again. So I appreciate that a lot. I applaud everybody's efforts, and I'm glad that you're putting so much into continuing to learn what you can with the remainder of the semester. So let's keep that momentum going with combinations. Today's scenario is a little bit different from the scenario in the last video. So if you remember from the last video, we were talking about chess club. So that of course is the first difference, it's a different club. But for the chess club, we were trying to select officers, right? We were selecting president, vice president, treasurer, and secretary. Or, you know, maybe that order wasn't correct for the secretary and treasurer part, but pretty much officers where the order was important. Today, however, we're going to be selecting a SpringFest committee. So if you read our scenario here, Computer Club is selecting a SpringFest committee. Okay, we've got a little bit of important information that maybe it would be helpful if I highlight it. So I've got my 3 members here, so that's probably important. And I also note that there are 15 students total in the club. So that's probably going to be important too. So I've got some important information here, and it's very tempting since we know that there's some sort of grouping thing happening that we might want to jump straight into permutations from before, but let's ask our very important questions from the last video. And those important questions were, is repetition allowed? And we had a question of order. Does order matter? Okay, and with the work, for example, with the Santa Anita race and again with the chess club scenario, order did matter. It mattered who I selected first because that person would take a designated spot for the chess club, it was president. For the horse racing, it was first place. So order did matter. Repetition wasn't allowed in either scenario because, you know, obviously if I'm racing a horse, if that horse comes in first, it is physically impossible for that horse to come in second, third, fourth, or any other place other than that, right? We can't double ourselves. So same thing happened with the chess club. If I'm selected for president, then I can't get selected for another role as a different officer. On paper, I'm the president and that's it. I can only really fill one position. So let's talk about computer club. If I'm selected for a committee, again, we run into this issue of me not being able to take another role in the committee. Now, my roles aren't designated in the committee, right? I've just got 3 people. 3 people have been selected to do the SpringFest committee. Maybe they're doing advertisement. Maybe they're splitting the job of who's bringing food or organizing food for SpringFest. Maybe they're trying to find some sort of product to celebrate their club. It's, you know, kind of like International Day. So these 3 people are responsible for setting up their booth for SpringFest. Okay, now, if this is me and I'm part of the committee, I certainly can't fill another seat in the committee. Okay, as much as many of us try to take on various roles and do a bunch of other work besides what is assigned to us, in the situation of needing committees, sometimes it's often that you need all the individuals that are involved with committee planning, with event planning. So if I'm already filling one seat, we can go ahead and assume that that person can no longer fill in any other seats. So are we allowed to repeat in this computer club situation? Our answer here is no. Hopefully you're saying no at home. No, we're not allowed to repeat because then we just wouldn't have enough people for the committee if there's a repeat. And again, we can't clone ourselves, so repetition not allowed. Now, what about order, right? Does order matter? It did in the past, so we need to really confirm whether or not order matters now, because a big part of your role in completing problems for Unit 3 is trying to answer these questions and decide, what am I supposed to use? Am I supposed to be talking about permutations where order does matter, as in the situation with the chess club and the horse racing? Or is it the situation where we're going to be using something called a combination where order does not matter? So let's take this scenario, okay? Let's say, for example, so here's our example committee. So this isn't really who gets chosen, because remember, there's lots of options here. But in our example committee, let's say we've got, we select Joe, we select Bob, and we select Sarah. Okay, so we've got Joe, Bob, and Sarah in our committee. Now let's say we didn't select Joe, Bob, and Sarah in that order, and instead we selected Joe, Sarah, and Bob. So kind of like when we talked about the chess club scenario, if I'm just picking names out of a hat, you know, let's say we decided everybody wants to be part of the committee, so we're just going to put names in the hat and draw names at random. It's the easiest, safest way to do that. If I'm selecting names at random and they come out in a different order, in this scenario, we still have the same committee. These committees are the same. It's made up of the same 3 people, and it didn't matter that Sarah and Bob showed up as part of the committee in a different order. It wasn't an issue at all. We could also have this scenario, and you guys kind of did this, right, with the horse racing scenario the first time, and you were trying to pick your winners. Maybe Bob comes out, you know, Bob's name gets pulled out of the hat first, and so we've got Bob, and then Joe, and then Sarah. And then with the same thought process with Bob being first, maybe instead Sarah comes next and then Joe. And then of course there's the possibility that Sarah is selected first, followed by Joe and Bob. And then maybe Sarah being selected first, instead Bob comes second, and then followed by Joe. And so again, just as with your box trifecta in our first activity with this permutations combination stuff, we have the possibility of 6 groupings where the committee is the same. Okay, so in this scenario, we have to be aware of the fact that if I'm trying to find out how many different committees can be created from this scenario, then I have to remember that it's possible that given a group of 3 people, they could come out of the hat 6 different ways and still make the same committee. Okay, so this is really important for the combinations thing, for you to be able to decide, do I use a permutation or do I use a combination? And the biggest thing is, does order matter, right? Because repetition didn't matter for either one. I'm sorry, repetition was not allowed for either one, but order does not matter the way it did before with the horse racing and with the chess club officers. Now we don't really care in what order people come out in. They're going to be representing the same committee. Okay, so let's see what this looks like mathematically. So let's start with thinking of the possibility. So I'm going to go ahead and erase this example committee, but keep them in mind. Keep in mind that given 3 people, we have 6 groupings that would produce the same committee. Okay, and so let's think of some examples here. So we've got, I'm going to make some boxes the way I did with the horse racing example, or I'm sorry, the chess club example. And let's consider member 1, member 2 of the committee, and then member 3. Okay, so we have 3 possible members to add to our committee. When I select the first member from that hat, and again, you can imagine this as, you know, random drawing of names out of a bowl. Maybe you write them on a little piece of paper. I'm sure many of you have done that. How many options do I have with, you know, or in other words, how many papers are going to be in the bowl as I draw for the first member? And hopefully many of you at home are thinking 15, right? All the students, the 15 students whose names are now in the bowl because they were part of computer club. So all students. And of course, after I draw one name, for example, Joe gets selected, right? So after I draw one name, how many names are left? I'm not going to return Joe's name on there. That would be strange. Because if I return Joe's name on there, then he ends up getting possibly chosen a second time, and then we can't have that because then we'll be short one person, right? He'll repeat the position, and that makes no sense. So leaving Joe's name out, now how many papers do we have left, right? And so hopefully in your imaginary bowl of names on slips of paper, with Joe out of the picture, we now have 14 students left. So this is starting to look hopefully a lot like the permutation stuff. So assume this is Sarah. Joe is selected, Sarah is selected, and then how many are left to choose from for member 3? That should be 13. Now you might be wondering, okay, so what's the difference, you know, between combinations and permutations? Because this looks a lot like the situation with the chess club. And the biggest thing for this scenario is that I need to divide the group by 6. Okay, so where did that 6 come from? Well, that 6 comes from the orders, right? The different orders. The different orders possible. All right, so the 15, 14, 13, I think is pretty straightforward for most of us. We know that those are the options available for members 1, 2, and 3. And again, I'm dividing by 6 because 6 eliminates all those repeated groups. Okay, so we had earlier in the video, we had the list of Joe, Bob, and Sarah, right? And we had 6 different groupings that represented really the same committee, just in a different order. And since we don't care what order they're in because they're all part of the same committee with the same responsibilities, we're gonna divide by 6. So we're really only counting one grouping. Okay, so in other words, this, Joe, Bob, and Sarah, Joe, Sarah, Bob, and so on and so forth. Sarah, Bob, Joe, Sarah, Joe, Bob. Instead of counting these all as separate possibilities for the committee, 6 separate possibilities, we're dividing by 6 so that really that represents one possible committee that could be pulled from the computer club. And that one possible committee has those 3 people in whatever order their name pops out of the hat. We don't really care what order they're selected in. Again, same responsibilities, not like with the president, vice president question from the last video. So dividing by 6 is really important. It eliminates all the different order possibilities that we don't really care about. Okay, that way we don't have as many possible groupings coming out of this problem. Okay, so turning to my calculator, I can go ahead and plug this in. So I'm going to scoot over some of our work here so we can keep working. And we end up with 15 times 14 times 13 divided by 6. And in my calculator, that is 455 possibilities. So possible, I should say possible committees. Possible, that way I'm staying. Actually, you guys are really good at writing complete sentences on your homework. I appreciate that. So I'm going to at least write my units here. So 455 possible committees could be taken if I need 3 people out of a club of 15 students. Okay, so this method is nice. It helps to know where all the numbers are coming from. We can see that 15 comes from the whole group, the whole computer club, and then 14 comes from after one member is selected, it's the 14 left over, and then 13 left over, and so on and so forth. So it's really clear what's happening in the context of the problem. And a lot of you submitted work that did just that. You used the numbers and you multiplied them carefully together instead of using the permutation rule. Some of you did both, which is cool. But multiplying them this way shows that you really understand what's happening in the problem. So that's nice. But let's consider the situation, for example, with America's Got Talent. Okay, let's say America's Got Talent. I think some of you seniors went and attended something like that. Let's say, for example, that they decide to give us tickets for 50 students. Okay, and we have, let's say, 800 of our Northridge Academy students decide that they want to go. Well, we can't take all 800, right? We were only generously given 50 tickets. So if I want to draw names out of a hat and I've got 800 students, right? So let me just jot some of these things down. So here's another scenario. So 800 students, and we are choosing 50. Now, again, we don't care about what order those students are chosen in, okay? Whatever order they pop it out in doesn't matter. We're just selecting a group of 50 in which, again, order does not matter. So that means it's going to be a combination. If I use this thought process on the left-hand side, then technically what I would be doing is how many students could be chosen. So I put all 800 names. Let's say we put it in a spreadsheet generator, and we're just going to have it generate at random because I don't want to draw 800 pieces. I don't want to write 800 pieces of paper. So we have this generator, and we click the generator. How many students could possibly come up first? And hopefully you're answering 800. And then how many students could pop up next? The 799 left over, and then 798, and then 797. And technically, I'd have to do this 50 times in order to accommodate for the 50 spots that I have available for America's Got Talent. In addition, I'd have to take those 50 students and rearrange them in as many ways as possible to find out what my denominator is. And I don't know about you, I know some of us have a lot of extra time right now because of the quarantine, but I am not about to start a list of 50 students in all the possible arrangements that can be made. So it would be lovely if we could have some sort of formula the way we did for permutations in order to tackle these more complicated combinations. And so let's see if we can create one together based off of the computer club problem. So we work with factorials, so let's start with factorials. Many of us, we saw 15, 14, 13, so we might be thinking 15 factorial, right? So that means 15, 14, okay, so I've got my 15 factorial shown in the numerator, but we didn't need 15 factorial in the numerator. We only needed 15, 14, 13. So really only this part is necessary. So I'm gonna try and do my best to find some way of eliminating all the rest of this problem, right? All the rest is 12, 11, 10, 9, so on and so forth. I need to find some way of eliminating that. Now, before I start eliminating that, don't forget about the 6 in the denominator. Okay, now 6 in the denominator. I don't want to write just 6 down there because I know something else has to be going on. And if I just write 6, it's possible that I'm not accommodating for other things. So let's stick with this factorial idea. And I'm going to change 6. I'm going to delete it. And I'm going to change it to 3 factorial. Now you might be asking yourself, well, why 3 factorial? Where did that even come from? Well, if I'm very careful with my factorial stuff, and I'm just going to make myself a little note here, 3 times 2 times 1 is equal to 6. And so that's equal to 3 factorial. Okay, so if I just start breaking things down into this list of numbers, it's our hope that we're going to find some sort of patterns happening. So now that I have 3 factorial, I'm going to go ahead and write that down here. 3 times 2 times 1. Okay, now it might be tempting to go ahead and start canceling things out, but if I start canceling things out now, then I'll end up with, so just so that you can kind of see where I'm thinking. If some of you are thinking, sweet, let's cancel out 3, 2, 1, then I have 12 through 4 left over, and that's not really a factorial because factorials go all the way down to 1. So maybe, you know, canceling out numerator and denominator stuff isn't the way we want to go just yet. And I'm just going to go ahead and deal with the rest of the numbers the same way I dealt with them in permutation, just to write them out. And make sure I do this on both sides, of course. So instead of rewriting this whole thing, we all know this is 12 factorial. So I'm just going to write here, let me put it in the back, 12 factorial. So now we've got our rainbow 3 factorial and then the newly added 12 factorial. Okay, and let's see if we can figure out where these numbers are coming from. Now I've gone ahead and accommodated for everything. All the 12s could go, and then all I would have left is 15, 14, 13 divided by 6. So that all works out. I accommodated for everything. And now let's see if we can adjust, figure out these numbers here. So let's start with 15 factorial. Where is that 15 coming from? And if we think back to our original problem, which, you know, hopefully you jotted down on your paper, you just have it in the back of your memory, this is our total student group. So total group, everybody involved in this club committee selection process, right? The 15 little names that were placed in the bowl or the hat. 3, where does 3 come from? Well, hopefully you're thinking that 3 comes from the number of students chosen. Okay, these are the kids that were selected. We need to take 3 out of the 15. And then finally, where's that 12 coming from? And hopefully this is kind of bringing back memories of the permutation material, which is all the kids not on the committee. We said last time, not meant to be in a mean way, these are our leftover students. Okay, so no offense to those guys, but those are our leftovers. And so again, we end up with this factorial situation that helps us figure out numbers without having to worry about making them up as we go, or without having to worry about large group problems. For example, the one I just said about America's Got Talent, where we needed 50 kids to go. Now we don't have to worry about thinking all through, and we can just use these formulas. So let's go ahead and formalize this formula for ourselves. So this is very important because this is going to be our definition for combinations. So when order matters, I'm sorry, when order does not matter, we use a combination. Okay, and so our combination formula, and again, it's going to look like this. Okay, similar to permutation, except now it's got a C for combination, and we're still reading it N choose K. We now have N, which is our group, right? So remember back from the last video, N is the total group. And we're dividing that by the kids that we chose. So number chosen. And to accommodate for our leftovers, we're doing the group minus the kids that we chose. Okay, and that's our formula for combinations that we can now use instead of worrying about filling in all the parts and multiplying all the numbers individually. Now we can use the formula. Of course, as I said before, those of you who are working out these problems with the smaller numbers and you're able to multiply each part and make the boxes and show the multiplication principle of counting and all that stuff, that's great because you're showing that you understand how the problem is working and what the problem means. But once we start getting into these large numbers, it might be more convenient to use this new combination formula. Okay, so in the last video, I know that I said you were going to have some ALEKS homework on this material, but when I selected the ALEKS homework in the last video, which was on permutations, the ALEKS assignment is actually on both permutations and combinations. So since I hadn't given you any support in that, I didn't want to make that mandatory, but it will be posted now because now you have formulas for both combinations and permutations. Before I let you go though, there are a few things that you might want to know about the ALEKS interface. So when we first started all of this combinatorics material, I made a disclaimer that a lot of stats vocabulary is not standardized, meaning some books use different notation, some books use different vocabulary. There's like things that are called the fundamental principle of counting rather than the multiplication principle or the addition principle. So there's a lot of things that the formulas work the same, but the vocabulary use is often different. So for example, I believe in ALEKS for permutations, they use, so we used P and then N choose K. Well, they use NPK, but ultimately it works the same. We still have N factorial over N minus K factorial, right? The group divided by the leftovers. And so same thing happens with combinations, okay? We've got on ALEKS, and I believe ALEKS does it like this, but I definitely know other stats books and combinatorics books use this. This one's N divided by K, I'm sorry, N factorial divided by K factorial times our leftovers. Okay, so really between combinations and permutations, this is the only thing that's new. Okay, and so even though that feels like it's the only thing, again, the numbers were very different. You know, that for the last problem we had 3,000 for the number of horses that could be selected, whereas with this problem we had only 455. So even though it only looks like a K factorial is a difference, it actually makes a huge difference. So be careful with that. As you read through the problems, make sure that you're just very careful in deciding whether or not order should matter or not, whether or not order should matter. And I think that's about it with combinatorics. So actually, this kind of closes up Unit 3 for us. Combinatorics is a very small unit, which it was just meant to kind of give you guys a taste of how these sorts of things work. I hope that you liked the material and I hope that you liked the activities. Again, I thought you all did an amazing job completing them. So this means that you are going to have a unit quiz soon. I would say sometime next week or the following week. So I would say that's good because now you're going to have another test grade in the test category, and if you do really well on this one, it's going to bump your test grade up. Again, those of you who have heard that your grades will not go down from March 13th, it does not mean that they can't go up. So I think this is a great opportunity for you to try and, boost your grades up by doing your part, taking your time, but also carefully managing your homework time. So You will be having a quiz on this soon. Look out for that. I'll give more instructions as we get closer to. And then after that, we get to start our finance, which would be really cool. We'll get to talk about budget, we'll get to talk about savings accounts, and I think it will be very useful for many of you. So, well, for all of you, really, we all need to deal with money, right? So again, any questions or comments or suggestions, I welcome them all. Feel free to message me and try and get in contact with me so we can work on things. As usual, just a reminder, period 1, Zoom meetings on Mondays. Now, they're not mandatory. They're more like office hours, which means I log in and you can feel free to log in and we can chat, or I can help you with homework problems that you might be stuck on. Period 1, yours are on Monday morning at 10:30, and period 4, I see you Wednesday mornings at 10:30. Okay, so just like if it was a 135 on Monday and a 246 on Wednesday, I have my Zoom available from about 10:30 to 12. So feel free to drop in if you have any questions or if you just want to say hi. But other than that, that's the material. That's the end of Unit 3. Again, you're doing great. Keep it up. Stay safe. And I hope to hear from you all soon. Take care.